-1. All right, hi. Math 234, multivariable calculus. You know the drill. We've got section 16.2 today, which is line integrals. The previous section, 16.1, was covered in a video because I want to spend as much time as possible on the line integration part, because I think that there's more going on there. But if I were to hit a super lightning round review of this section, we look at vector fields, which is just we take our standard 2D plane, or maybe 3D space, and every point gets assigned a vector instead of just it being a point. That point isn't necessarily its position, or that vector isn't necessarily the point's position vector. It could be some field, usually one that's described by an equation. In this particular example, the field is negative yx, but it's given as a function that generates vectors based on the point in space we're at. Then there was a whole bunch of fancy stuff going on here where we talk about going from 1, 2, or 3 dimensions to 1, 2, or 3 dimensions and the functions that happen in that way. So going from 1, 2, or 3 dimensions are all of the standard functions that we are used to, right? Just our scalar functions that take x and turn it into a y value, or take x and y and turn it into a z value, or take x, y, and z and turn it into some value we haven't super talked about yet. That's fine. We'll get there. The number of dimensions we're coming from dictates how many parameters we have. So x for 1 dimension, xy for 2 dimensions, xyz for 3 dimensions. Then going the other way from 1 dimension up to multiple dimensions, those are the parameterizations that we've looked at. Right, if I start from just 1 dimension and end up in 2 or 3 dimensions, I've got some sort of curve that I've parameterized, but I only needed a single parameter to talk about it. And then that leaves the other super fun translations. Mostly we just need to focus on 2 to 2 and 3 to 3, and those are going to be our vector fields. So a vector field in 2 dimensions is one that sends a coordinate point xy to a vector, also having 2 parameters. We usually call them P and Q. So the results, when we start trying to talk broadly about our vector fields, one of the, hey, now I don't know what you just did over there, but I would appreciate it if you cut it out. Okay, thanks, computer. And if we're in 3 dimensions, PQR for the X, Y, and Z components. The rest of that is a super fun looking thing that we'll dive into some later on, but also more in that video. We have these conservative vector fields, which is probably the most important thing we talk about in that section, but we're not going to talk about it today because that's going to be way more important on Monday's class. And then a couple of examples of just trying to visualize what 3D vector fields look like. In particular, this last example is one that I do want to come back to today, but I'm going to save it for right now. I'll wait till we get there. So vector field, or nope. We just talked about vector fields. Line integrals. Let's bring some stuff up. All right, come on. There you go. So, one of the things that I think is probably most important to talk about at the beginning of integration in multivariable calculus, which as it turns out is right now, are our integration tokens, or our differentials. All through Calc 1, basically the only differential we looked at was dx, right? Or I sometimes call them an integration token because it's the thing that you have to spend in order to do an integral. And we kept telling you back in Calc 1 that it's always super important to put that dx on there. But then kind of we never did anything with it because it was just like the thing that you had to write down. Usually the explanation goes something like it's the piece that tells you what your variable is. But again, despite the fact that we said it was super important in Calc 1, it kind of never ended up really mattering, right? Like you could still calculate an integral even if it wasn't there, if you were willing to, not do the math exactly correct. Which then totally fine. But today, those are important for some reasons that we should talk about. Because when we start looking at these line integrals, just skipping ahead for a second to this arc length calculation down here, I have that the arc length is the integral of 1 times ds, which is a new differential that we haven't particularly seen before. But it's going to come from some sort of parameterization of our curve C. In fact, we don't necessarily need that parameterization. We just need ds to represent the curve somehow. So let's start back in Calc 1 to remind ourselves how we decided on dx as a thing that we needed to throw in there. We built up integration from our infinite Riemann sums, which was taking some area under a curve, subdividing it into a ton of rectangles. We're going to claim that the width of each one of those rectangles is going to be a regular fixed value that we'll call delta x, just the change, the width of our rectangle. It's the change in between subsequent x values. We take a limit as the number of these rectangles goes to infinity, which means that delta x gets close to 0, right? It's supposed to shrink to be really, really small, but we don't want it to be exactly 0, just like we never wanted to divide exactly by 0 when we did derivatives. So that delta x has a limit of dx, our differential, our integration token. And that thing is supposed to represent an itty bitty tiny little change in the x value. All right, so if I'm looking at the way that dx operates, delta x again being the width of each of those rectangles, dx is just a little itty bitty move along the x-axis. It represents super small change in x. So that when I integrate over dx, I'm integrating over those tiny little itty bitty changes, of which there are an infinite number because I'm taking that infinite sum. There's a ton that you could get lost in there, but let's pull ourselves back. Just thinking about little tiny change in d in x. That's what dx is. So if we start trying to upgrade that stuff to other variables, like dy would be a little itty bitty change in the y direction, dz, little change in the z direction, dt, we've already used those, I think, when we looked at some stuff earlier, didn't we? No. Line integrals is right now. I'm remembering preparing for this lesson. Scratch that. So dt, sort of its natural extension, should be a little small change in the t parameter. But t isn't necessarily one of our axes that we're throwing up in 2D space, or in our 2D plane, or in 3D space. So it's got to represent some other little small change somewhere, right? Oftentimes when we make our parameterizations, we'll just say that we're going to start at t equals 0 and go to t equals 1. So then that little interval that's somewhere in t space would represent where t is changing. But for a line integral, we're going to be integrating along some curve that's out in space. Could be just in a 2D plane, like I suppose this example is here, but ultimately we want to be able to throw this thing up into 2D space, or in 3D space. Yep, there we go. I'm feeling real good with numbers today. And I want to kind of use that same idea, right? ds should come from delta s being a small change in the arc length, or a small change in the length of the curve that I'm moving through. If I were to try to, split my integral up over here, I can see with z being the extension of some sort of curve, I'll add up a whole bunch of stuff over there. But again, that delta s is still going to represent the width of some kind of a rectangle, just like delta x did. My rectangles are just now curving through space, but that's gonna be okay because we can still take some infinite limits to get them back down to some super small value. But the same thing ought to happen with ds, where it should be a small change in s, or a small change along the curve, in the same way that x would have been a super small change along just like the x-axis. When we start parameterizing that curve, which usually ends up bringing it back to our t parameter, I still want to think of t as just operating smoothly along some interval. So if you see down below that graph, below the 2D graph I've got there, might as well just go highlight this thing, right? This spot right here, that's showing t just changing along an interval. And then those small changes in t, which is actually going to be our integration parameter when we start trying to do some stuff with the math, should translate to some sort of small change in the curve. I want to be able to relate dt up to ds, right? Where I can look at a small change in my parameter and see how it impacts a small change along the curve. And with that in mind, we're going to start using and paying a lot more attention to the particular differentials, or maybe again, think of them as integration tokens that we're putting into our integrals. Because it's going to start mattering a fair bit more, because we'll need to translate between the physical object that we want to be integrating over, or well, physical object, or graphs in a math world, but taking that object where I'm integrating along, some curve or some surface later on, or possibly even a solid, if we're feeling spicy, and be able to translate that into the change in a parameter, something I can actually integrate over. So what I might do over here to just kind of grab the arc length as a value, parameterize my curve, where I'm going to parameterize it in terms of t, again, so x of t and y of t. S is going to be the arc length of said curve, and I know from back when we did the arc length section, we have done integrals with t. Knew it was somewhere. We had to take integrals to do arc length. I knew that. So we're going to integrate the magnitude of r prime. That was our formula for arc length back then. And it turns out the magnitude of r prime is just the square of the derivatives of x and y added together, and then take the square root of that, because we've taken the square root of vectors before. So we got that bit. So the arc length should just be the integral of that square root dt, which is going to give us a way to relate ds to dt. Right? If I go take a derivative of this thing again by the fundamental theorem of calculus, which is the one of the fundamental theorem where we had like two halves. One is just the integral is f of b minus f of a. We got that one. But the other one said that if I take the derivative of an integral, I come back to the integrand, the thing that's on the inside of the function. So if I say arc length is this integral, and then I take the differential of that, I get that ds is conveniently this square root times dt. That's going to be our motivation for pretty much the entire rest of the day. And probably also Monday. But we'll worry about Monday when we get there. To bring some things back up from over in the typed out notes, I think this is all kind of still the same stuff. Although maybe I want to go give a slightly new integral value over here. If I know that I have a parameterization that goes from a to b, then that arc length integral ought to be the square root of, let's call it x prime squared plus y prime squared dt. Again, highlighting that my differential is going to change from integral to integral, and it should be telling us something a bit more important now. Instead of just, hey, your variable is whatever letter, now we're going to use these differentials to actually describe what object in space we're referring to, ideally. Next section from the pre-class video talks about some stuff that's in chapter 15 that we haven't gotten to yet. think that that's just an artifact from when we used to teach the textbook in order instead of the, super fun order that we do now. So you can safely ignore that for a bit. We might talk about it when we actually return to chapter 16 after we do chapter 15. So a line integral. So I spent a bunch of time defining that arc length thing a moment ago because I thought it was going to be important. I was right. If I want to have the the line integral of some function along a curve again being some c, then it's going to be the integral of f times ds. The integral of f ds. So ds, again, our differential or integration token for moving along the curve. And I'm just going to slap a function in front of that. If that function is 1, the line integral just returns the arc length, as we saw a moment ago. But for some other broadly defined function, I can just get a line integral where I plug something in and try to integrate it. One thing worth pointing out here, I am parameterizing my curve. So I just have one parameter, so we're just doing one integration, right? My one parameter. It might be translated into 2 or 3 dimensions, depending on whether I've got x and y or x and y and z. But I've only got the one parameter, so I'm only doing one integral because I'm going along a curve. I'm really emphasizing that right now. Before too long, we're going to start looking at making that a lot more complicated. For today and Monday and all of the content that's on exam 1, just integration on one parameter. Promise. The box below that, the other one that's on screen, is the one that shows what we're looking at in 3 space, where I've got x, y, and z instead of just x and y. But the one that I've got highlighted here, with the fancy looking green stars down there, is the one that I tend to just remember most of the time because it generalizes for any number of dimensions. So the line integral of f ds is the integral of f of r of t, right? Where I just parameterize my curve for however many different components I might need to have. So it's just f of r times the magnitude of r prime. And that's probably the version we'll use the most. A very quick overview of what a problem like that would look like. I figure out my function is, which I kind of cut it off the top of the screen, so let me pull that back down. My function is that p of x, y, z, and I want to do the integral of that ds. That's my fundamental idea. I'm integrating along a curve. ds is my small change along said curve. And then I parameterize that thing and rewrite my integral all in terms of my parameter t. Once I get my parameter, or my parameterization, which includes my parameter, I should now have bounds for my integral. In this particular case, we know we're going to go all the way around a circle, so my bounds are 0 to 2 pi. You'll notice I've switched from ds over to dt, because now I'm looking at small changes along my parameter instead of along my curve, but I'm translating those small changes in my parameter to changes on the curve via the magnitude of that parameterization tangent vector. In this particular case, it's a circle of a radius with 1, so it had a very nice magnitude, just 1 in there. Also, I substitute in for x and y and z based on my parameterization, x of t, y of t, z of t. So plug some stuff in, ta-da, there it is. Do an integral, and I got an answer. By the time we switch over to dt, we're just back to our regular first and second semester calculus integration methods. ds is our new idea where we want to be moving through some curved line in space. But by the time I get to my parameterization, it's just a standard integral. So we want to at least be able to rely on the methods that we've already learned to work with this stuff. So, okay, let's go do that. So, as an example, I've got a wall that can be parameterized by the curve t sine t, t cosine t for t in the interval 0 to pi. Don't forget to put bounds on all of your parameterizations because that's going to be pretty critically important over the next couple of sections. But I know the height of this thing. Apparently, we decided that this portion of a wall is not just a wall, but the Great Wall of China. So the height is given by some function. We know each brick has a cross-sectional area of 100 square centimeters. How many bricks are needed to build the portion of this portion of the Great Wall? So let's go calculate that, right? If I imagine this curve over here on the right to be my segment of the wall that I want to build, the total area of that wall should be roughly the height times the width because it's kind of rectangular, but we want this thing to be an integral. So we're going to be looking at the integral of, that's like the worst integration sign I have ever drawn. I want the integral of h of x and y ds over my curve C. Right, that'll give me the area of the wall that I'm building, total area that's there. I'll come back and answer the question about how many bricks I need later. First, I want to figure out the total area I need to make the thing, and then we'll worry about that cross-sectional area of each brick later on. So I've got this part all ready to go, but before I start actually trying to do my integral, I need its individual pieces, which means finding a parameterization and then finding a tangent vector for that parameterization. And at least if I'm integrating a scalar function, which this is, I need the magnitude of that tangent vector. So far, we've already got our parameterization, so I just need its derivative. R prime of t. What's it gonna be? Angled brackets for a vector. That looks like 2 cosine t. Oh, 2 cosine t. Negative 2 sine t. And that's still for t in 0 to pi. I already have that bit. So now let's go get the magnitude of that vector, which is not a vector anymore. Magnitudes are scalars. This looks like 4 cosine squared of t plus 4 sine squared of t. Put a hat on my square root. And then this thing simplifies rather nicely to just 2. Right? Sine squared plus cosine squared is 1. That's one of our trig identities. Sort of the one that we use the most often, though there are a few others that will be coming up in the web work from time to time. But that's like the super most interesting one. So the inside of that square root is just 4. And of course, the square root of 4 is 2. So we'll go with that. So now that I've got the magnitude of my tangent vector, I'm ready to start plugging some stuff in. So my height function, it's x times y squared, which looks like it's going to be 2 sine t times 2 cosine t, that bit squared, multiplied by the magnitude of the tangent vector, which we got to be 2 dt. And again, I'll keep highlighting that in green for a little bit to emphasize that we're changing our differential. So our variable is switching. Also, I know my bounds for this integral are 0 to pi And I can just draw a little arrow that says, hey, look, bring this 2 down. Also note that we went with a somewhat non-standard parameterization for this arc of a circle, since we've got sine in for the x component and cosine in for the y component, which would probably mean I'm doing something like starting at the top of the circle instead of starting over at the standard right side of the circle. Right? Normally in standard position, we start from the right side and go counterclockwise. This particular parameterization is starting from the top and going regular clockwise. I hope I drew that right from your perspective. Yeah. Fancy stuff. We'll talk about that again later when we have to do our own parameterization. But for now, I think we can just go try to integrate this thing. So let's see what we got. There are a lot of 2's. So I'm just going to pull them all the way out. I've got 1 2 from the sine term. I've got 2 from the cosine term. I've got another 2 from the orange term. I think that's 16 because there's 4 2's in total. And you might know I'm writing an over 3 here right now. But I've basically got to integrate cosine squared times sine dt. So a quick u substitution will tell me that u is cosine, du then is negative sine. So that ought to integrate to cosine cubed t, where I need to evaluate from 0 to pi. And I believe that this has a mistake in it right now, as I've written it out. I'm totally testing you this time, and not just because I missed it. I slide you just a little bit over to the right. I said if u is cosine, that means du is negative sine, and I don't have a negative sign in my integrand, so I'll need to make one. So this thing should be negative 16 over 3 times cosine cubed, evaluated from 0 to pi, which if I go and do that integral, negative 16 over 3 times, let's see, cosine cubed of pi. Well, let's just ignore the cubed for a second. Cosine of pi is negative 1. Cubed is still negative 1. Minus cosine of 0 is 1. Cubed is still 1. So negative 1 minus 1 ends up being a negative 2. And then negative 2 times negative 16 over 3 is positive 32 over 3. We know we were expecting to get an area out of this calculation. So if I do all my work and I get a negative answer somehow, probably means I've made some small mistake with a sign elsewhere in the problem. So it is usually worth thinking about some of these by the time you're done with them, making sure that your answer makes some amount of sense. We probably don't expect to get a negative area for the wall that we're building. So that is 32 over 3 square meters. All right, if we come back up to the top, our height is given in meters. And also, since we weren't being as careful as a physics class probably would have been, the portion of our wall didn't ever actually get units. But I believe we're meant to assume that R of t is also given in meters. So when we maybe just add that in, I'm supposed to have meters right there. And I'm calling particular attention to that because when I go to calculate the number of bricks, it's worth noticing that my bricks cross-sectional area was given in square centimeters. My number of bricks would be 32 over 3 square meters divided by 100 square centimeters per brick, which is going to end up being, I think, 3200 over 3. If I convert those square centimeters to square meters, I'll get a number like that. And then I can approximate that to 1,067 bricks. I think a quick scan of your calculator will tell you 1066.666, repeating, of course. So I'll just round that up to 1067. All right. Let's go look at another one. How heavy stuff is in a density function. So suppose I have a nice spring. Curve is given by that parameterization. I know its density function. I want to know how heavy the spring is. Again, I should probably assume that my curve is given in units of centimeters since my density is given in grams per centimeter. Just to like keep us honest over here. What do I want to do? Well, I've got my parameterization already, so I should calculate its derivative. R prime of t looks like it's going to be 3 cosine t, negative 3 sine t, 4. Again, notice sine and cosine are backwards from our usual parameterization. Also, t is a bit odd. We're going from 0 to 8 pi. If you think about how a spring works, that ought to make sense. A coiled spring is probably going to spin around itself several times. So if this thing goes from 0 to 8 pi, that means our coil has 4 full revolutions. Since a single revolution would be 0 to 2 pi, this goes from 0 up to 8 pi, which I am pretty sure is 4 times 2 pi. So 4 revolutions on our spring. Now that I have the tangent vector, I should calculate its magnitude. So magnitude r prime is a number. This is going to be 9 cosine squared plus 9 sine squared plus 16. And conveniently, that's a Pythagorean triple. My result's going to be 5. Again, sine squared plus cosine squared is 1, which means 9 cosine squared plus 9 sine squared is 9. And then 9 and 16 is 25. Root 25, just 5. And with that in mind, I want to go get the weight of this thing. Except I don't want the weight, do I? This is in the metric system, so I actually want the mass. Since I'm giving grams per square centimeter, that's a mass unit, rather than pounds per square centimeter, which would be a weight unit. Or newtons if I wanted to stay metric. But yeah, we'll call that the mass of this object is equal to the line integral of the density function times ds. Right, so if I just integrate my density over the curve, I ought to come up with the mass of the object. So, start plugging some stuff in. This is the integral of my thing. The density function is the thing in question here. This will be 10 minus x, which is 3 sine t, minus 3 cosine t, which is y, all that times 5 dt, 0 to 8 pi. Again, highlighting some of that stuff in green, so I know I'm back to my parameter. And again, here's some whispers out there. So if You know, if you have a question or if you found something wrong with my work, which is usually the case when I hear that many whispers. Didn't really grow though, so I'm assuming that part's all right. And now from here, I'm going to use a few rather handy integration techniques that I recommend that you refresh yourself on if it's been a minute. So if I multiply that 5 through, I'll get a 10 times 5, which is 50. 50 ton. That's just a constant integrating from 0 to 8 pi means I'm going to get 50 times 8 pi. Now, for integrating definite integrals of sine and cosine, our harmonic function, or cyclical function, these two things oscillate up and down, where if I look at a complete revolution, I have some of my area that's above the x-axis, some of my area that's below the x-axis. And this thing, again, harmonic functions, very symmetric. If I look at an integral over a full period of either sine or cosine, my result's going to be 0. Because I'll have just as much area above the curve as I'll have below the curve. That's still going to hold true if I do 4 revolutions, right? Each revolution is going to give me a total area of 0. So that would just be 4 times 0, which conveniently is still 0. These are being subtracted. So I'm going to go minus 0, minus 0. And I'll use that trick a fair amount when I'm integrating trig functions. I'll show you a few others as they come up as well, because they are very, very nice time savers. When you're already dealing with a bunch of other really complicated stuff, it's going to be nice to take shortcuts when you can, especially if that just can, you know, relieve some of your mental load to not have to think too hard about some of the integration we're doing. So integrating a trig function over its full period is 0, which means this thing comes out to 400 pi. And that'll be in grams. Oh, wow, that's cool. I am totally going to finish the whole lesson today. So, fun. Okay, right. I just brought up a new screen. I should introduce it. So, what do I want to say here? Thus far, we've been calculating line integrals of scalar functions, right? Where I've been integrating along a curve, which that part will still be true. We're still going to be integrating along curves, but the functions that I've been looking at, particularly the last two, they were both scalar functions. The height was x times y squared. The density was 10 minus x minus y. Again, scalar values. The result of that function is a one-dimensional answer. It's just a number. If I'm looking at specific function values. The reason we spent all that time bringing up vector fields in the previous section was so that we could integrate over vector fields. So, a second version of line integrals. There's going to be 2 that you'll need to know. And if you think that's bad, just wait till later. 2 versions of line integrals. We're going to apply them differently, and it's all going to depend on the type of function that we have. If we have a scalar function, we'll be using the previous example, where we're going to convert ds into a scalar multiple times dt. But if we have a vector valued function, is the thing that we want to integrate, we won't end up needing to calculate that magnitude, because instead we'll just take a dot product of our field with the tangent vector. And in particular, we want to be looking at the dot product of our field with the unit tangent vector. And that's going to be important for the derivation of the formula, but then once we actually start working with it, we'll find we don't really need the unit normal or the unit tangent vectors. The regular tangent vector will do. The reason for that, if I check out this section right in here, when I want to take the dot product of my field with the, again, unit tangent vector, I get a magnitude of that tangent vector in the denominator. But I also know when I'm converting ds into dt, I want to multiply by the magnitude of that tangent vector. So if I start trying to simplify that expression, I think those two magnitudes should resolve themselves to just being multiplying by 1, which gives probably the best and most convenient version of this second form of a line integral, which is just going to be our field f dotted with dr, and I just saw that I missed a parenthesis. Mr. Brandenburg would kill me if he saw that. But that's fine. He's not here right now. So yeah, we're going to take the dot product of our field with our just tangent vector for the curve that we've parameterized. No need to actually calculate the magnitude of that tangent vector, at least not right now, because again, I'm going to have a magnitude in the numerator and a magnitude in the denominator. So as several people are fond of saying, those two should just cancel. It does have a few other forms though. Its maybe most theoretical form is the dot product of the field with the unit tangent vector, capital T, ds. Right, we're back to using a ds in that particular version of the line integral formula, and also written out probably the most quickly. So the easiest shorthand notation we've got is f dot dr. Where dr is the differential in the curve direction. Really, dr is just going to be the derivative of our parameterization pretty much all the time. And in fact, in the next two examples, we'll see that we're going to rely on that rather heavily. Okay, so if my field is a 2D field, then it's just going to be PQ. I can have my parameterization, which is R, then f dot dr can simplify to a scalar integral of just the integral of p dx plus the integral of q dy. Noticing here that dr, right, if r is xy, where again x and y will be functions of a parameter t, but I left that detail off to simplify some of the notation down. If x is xy, dr is dx dy. So if I take the dot product of my field PQ with dr, dx dy, I get p dx plus q dy. That part right there. And I can step that up to 3 dimensions as well. My field is PQR. That means that r is x, y, z, and dr is dx, dy, dz. When I take their dot product, it comes out to that equation you see at the bottom of the screen. So p dx plus q dy plus r dz. So there may be times where it's convenient for us to start from the f dot dr form and just take the dot product out to this rather nice PQR scalar integral. Because in the end, I just want to be integrating scalars. By the time I actually get to the work of the integration part, it should be a scalar value, which is why I've got dot products of vectors when I start working with vector fields. But I should again come out to this PQR result. It's just a scalar value. Also, there may be times when we want, maybe we're given some integral here, p dx, p dy plus r dz, and we want to work it backwards to get the field. And if I want to do that, I can just pull the dx component, the dy component, and the dz component to generate my p, q, and r that should go back into the field. That might be helpful in a web work problem or two, and I think I put an example of it at the end of the lesson. So right, I skipped over the last part, which said that this is super important for work. Work being the physical quantity work. In your introductory physics class, we would have called this just force times distance, at least before we introduced calculus into the mix. For the full and proper definition of work, it is the integral of f dot dr over the path that the object is moving. And to just kind of highlight a bit of what's going on here, where d here is the displacement vector, work should be the dot product of those two, as long as my displacement is constant. So if we look at work at a point, I'm going to call that the dot product of the field with the tangent vector. Field and unit tangent vector together. It should give me my work at a single point, putting that kind of in some air quotes. So if I just come over here and, I don't know, maybe draw a field, which might be doing something erratic or chaotic. All those blue lines representing the field that my, whatever this object is going to move through. And maybe in particular, I'm interested in some of these field lines when they are near the curve. So I don't know, how about like this? And then let's say we go that way. Held it too long, maybe that way. And then also come in and look at some of my tangent vectors. Oop, which I think will be here. I think that tangent vector should be under the curve. So tangent vectors here drawn in green, force field drawn in blue. I'm looking at summing up a whole bunch of these dot products as I go through to figure out my work formula. And here is the spot where I do want to call back to the previous lesson, which was 16.1. That very last page when we were trying to convince ourselves that the force would be acting in some certain directions. If I want to maybe figure out if this field is helping move the object or not, I want to look at the field lines in relation to the tangent vectors. In this particular case, I just have straight lines, so my tangent vector is just one convenient line that points all in one direction. And I found that my work ends up being, or my integral is going to end up being negative if my movement is in the opposite direction of the forces, broadly construed. And my integral, or my work, will be positive if the motion is broadly in the direction of the field vectors. And a real big reason that's going to happen is looking at the dot product of two vectors and comparing it to the cosine of the angle that is between them, which I'll have just enough time to write that down before I'm out of time. So what did I want to say here? Well, I don't have the field in yet. Yeah, so notice, nope. All right, here's what we're going to do. I am just going to take this over to the completed version of the notes to just highlight a couple. Don't be like that. Okay, fine. Fine. Here we go. To just talk about this one last example before we go. Drew a curve in, again, looked at the force vectors and some tangent vectors. Along that curve, the angle between all of my vectors is acute. But if I'm looking at the way that the tangent vectors interact with the force vectors, very near that curve, I drew some of them in a slightly larger font. All of those angles are acute, which means that the dot product, which is really just a couple of magnitudes times the cosine of theta, is going to be greater than 0. Because cosine theta is greater than 0. Meaning the work in this example would be positive. All right. let's continue on with the last couple of examples. For still integrating, doing line integrals of force fields. I guess just line integrals of fields generally. Force fields just happen to be the nicest examples to work with. So find the work done by the force field, that thing, in moving a particle along the quarter circle of x squared plus y squared equals 1 from 0, 1 to 1, 0. Notice, if we just compare to the part above, I've got the same arc of the circle, which I kind of glossed over drawing it, but that's the orange curve drawn in right there. That is the arc of a circle from 0, 1 to 1, 0. That, again, that circle being centered at the origin of the radius of 1, so it's like the unit circle. But notice that we're starting at the top and we're traveling counterclockwise. Nope, we're traveling clockwise to get to the right side. Right? Normally we travel counterclockwise. This time we're traveling clockwise, which means our standard parameterization of x is cosine, y is sine, go from 0 to pi over 2 is not going to work for us this time. Because we kind of need to do the opposite of that. If we stuck with that parameterization, x for cosine, y for sine, we'd be traveling from pi over 2 to 0 for my parameter t, which I suppose like could work. I think you can set up an integral that way. You'll just have to notice that you're integrating backwards, which can introduce some complexity, but it doesn't need to. So I think there are two pretty valid ways of setting up our parameterization here. Either go with your standard x is cosine, y is sine, but then integrate from pi over 2 to 0. So integrate backwards. Or the last few problems have been suggesting a new parameterization to use, which is not going to be written down just yet because my pen ran out of ink. So awesome. Give me 1 second to apparently refill it. Hey, look, it's totally fine. Who would have guessed? All right. So I want to do some new stuff, which is going to be to create a parameterization R of t, which is going to be sine t for x, cosine t for y. And that'll leave our usual curve for, or more usual bounds for t of 0 to pi over 2. But now t of 0 is going to be at the top of this circle, and t equals pi over 2 is going to be at the bottom or at the right side of this circle. So this guy up here is t equals 0. This guy is t equals pi over 2. And then conveniently, my starting location is still tied to a parameter of t equals 0. So again, we're just rewriting the thing because we're traveling the wrong direction. We're traveling clockwise instead of counterclockwise. So I'm going to set up my parameterization this way. And I'm going to go get r prime of t, which is cosine t, negative sine t. And then if I were just going blind, I would probably calculate a magnitude here, which is, I'm just going to jump ahead to that magnitude is 1. And maybe just move this over to the side for a second. Right, because that's how we've been doing it so far, was calculating a derivative and then getting the magnitude of that derivative. So maybe I just did it because it seemed like fun. And I now want to do a part over here. I'm looking for the work done. So the work, capital W, is going to be the integral of f dot dr over my curve C, which for us is going to look like the following. It's a couple of vectors. One's a vector field, the other's a tangent vector. This is going to look like sine squared of t negative sine t cosine t. Dotted with my dr vector. Cosine t, negative sine t. All of that times dt. Or all of that dt, I guess. My bounds are 0 to pi over 2 because I only want the quarter circle. And then let's go get a dot product, which is going to be another integral. This time it looks like sine squared cosine plus, well, looks like I get sine squared cosine again. Sine squared t cosine t. Still dt. Still from 0 to 2 pi. And conveniently, this means I only have to integrate one function in there. Looks like another fairly decent looking u substitution. So I'll set u equal to sine t. That means du is cosine t. Conveniently, I've got all of those parts already there. In fact, du is cosine t dt. So I'm just going to integrate u squared, which will go to u cubed over 3. So this looks like 2/3 times the sine cubed of t. And I want to evaluate that from 0 to pi over 2. Which looks like 2/3 times, well, sine of pi over 2 is 1 minus sine of 0, which is 0. So I get 2/3. And just to kind of check some things for ourselves here, we spent some time previously making sure that our work should have come out positive here. So we're going to be relying on some of that idea quite a bit as we go on. For now, we're just using it as a sanity check on our answer. We know we should get a positive value once we're done, and we did. We got 2/3. So we feel fairly good about that answer. Also, I kind of alluded to it earlier. I never actually used this magnitude, right? The r prime of t having a magnitude of 1, that didn't come up when I integrated a field because I just ended up taking the dot product with the tangent vector directly instead of needing its magnitude. So I mostly just put that on there to emphasize that we don't need the magnitude when we're doing field integrals. Yeah. And cool, yeah, this is the last page. So let's go do this one. So what we're gonna do this time, I've got another line integral. This time it's already given out in that PDX QDR. Yeah, PDX QDR RDZ QDY. There we go. One of my letters wasn't working out. So if I were to just go look at what that field should be, because I think it'll be worth having at least one example where you've seen how to figure out the field. The field should be Y for the X, Y for P, Z for Q, and X for R. This one is R right there. This one is Q. And that one is P. Again, might be worth trying to reverse engineer that, I think, on a couple of web problems. Right, this time we've got 2 line segments. Our curve C is a C1 and a C2. So I'm going to have to make 2 separate parameterizations. Along C1, my parameterization vector R of t is something. If I want to go from 2, 0, 0 to 3, 4, 5, I need to go over 1 in the x direction, 4 in the y direction, and 5 in the z direction. So all of that times t. And my starting point was 2, 0, 0. Just slide that a little bit to the right because I still need to say that t is going to be in 0 to 1. So that's my line segment. Gets me from one to the other. Notice that if I plug in 0 for t, I get 2, 0, 0. If I plug in 1 for t, I get 3, 4, 5, which was our goal with one of those parameterizations, or with one of those line segments. R prime of t then is conveniently just 1, 4, 5. It's just the vector that's stuck to t. Kind of like the slope of that line. I'll also have a second curve, C2, where my parameterization is going to look a little different. This time I'm going to go from 3, 4, 5 to 3, 4, 0. So if I look at my direction vector, I need to move 0 in the x direction, because I'm already at 3 and I'm staying at 3. 0, nope, try again. 0 in the y direction, I'm already at 4 and I'm staying at 4. And then -5 in the z direction, because I'm starting at 5, but I need to end at 0. So that's my direction vector, 0, 0, -5. And I'm starting at the vector 3, 4, 5. And my bounds for t are still 0 to 1. R prime of t is 0, 0, -5. Nice thing about line segments is that their derivative is just the direction vector. And now we're going to go calculate a line integral. So I want the integral of, how do I want to write that? I'll just call it f ds. No, it would have to be f dot tds. Yeah, let's call this the integral of PQR. Let's do with it that way. PQR dot dr over C is going to be two separate integrals. There's one that's got to be over the curve C1, which is going to look like whatever that field was, y dx plus z dy plus x dz. And then I have to add to that, me being extra lazy and copying and pasting the previous work, but changing that C1 to a C2. All right, so I'm gonna have to look at the work or the integral being done first along the green line segment, and then the line integral being done along the blue line segment. Conveniently, when I turn these things over into their parameterizations, they both have the same bounds for t, both between 0 and 1. So I can combine their integrals into just a single house. So we're going to integrate. Let's try again. We are going to integrate from 0 to 1 of a bunch of stuff that's about to get plugged in. So let me zoom out so I've got everything in at once. Along the green curve. And let me just come back up here and color in a couple more pieces. I want that part to be in green and that part to be in blue. Just to emphasize that's where I'll be pulling some stuff from. The y value along that green curve, y dx. Y was 4t plus 0 times dx, which is 1. Plus, I need a z value, which is 5t, times dy, which is 4. Right, I'm pulling that from like a 1 right here and a 4 right there. plus I have an x value, which looks like it's 1t plus 2 times dz, which is 5. So that's the green curve. Adding to that, I want the blue curve, which y is 0t plus 4 times dx, which is 0, plus z, which is negative 5t plus 5. But that is multiplied by dy, which is also 0. And the last part of this super fun and long, exciting integral is another number. Where'd it go? Where'd it go? Where'd it go? X, which is just 3, times dz, which is negative 5. Slap a dt on the end there. And then the last step is to just integrate that whole thing. It's a definite integral, so it's going to come out to be kind of nice. This will be 4t squared over 2, evaluated from 0 to 1, which will be just 2. So I'm going to be dividing it by 2 there. Blah, blah. 20t integrated from 0 to 1 is going to be 10. 1t plus 2, or rather 5t plus 10 is going to be 5 over 2 plus 10 when I evaluate from 0 to 1. Plus both of my next two terms are 0. But finally, I am integrating negative 15 from 0 to 1, which is negative 15. And then I simplify all of that. 22 minus 15 is 7. 7 plus 5 halves, 14 halves plus 5 halves, 19 halves, I think. Cool. So in the end, we found that the work is 19 over 2. That I think is the thing I want to say there at the end. All right. And as a final, just quick note, I know that it's been a while already, so I just want to highlight there's a couple of other things I included over in the margins. Started one-line integral problem, one that I think is a little tricky, but is relatively straightforward to explain, at least just by looking at what's going on. So here's just another example of a parameterization. Find it in the notes. And maybe a couple of other things up here. Oh no, we talked about all those already. Never mind. Cool. So I will leave it right there and call it a day. Okay. Bye, 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 bye.